for grabbing coffee. It's my pleasure to introduce you to YY. So YY is an associate professor at IU, Indiana University. He was a visiting professor at MIT. And before joining Indiana University, he worked as a postdoc at the Center for Complex Research at Northwestern University. He has very, very interesting research. His papers are really nice. If you see the pictures and the drawings are just amazing. So if you haven't had the opportunity to read his paper, I really encourage you, not just by the quality of the science that he does, but the care of making like the plots really, really beautiful. So YY will talk to us about unreasonable effectiveness of neural graphs embedding. He has very nice works with graph embeddings, frame axis, and many other things. I won't take his time. Please, YY, the floor is yours. Just one more thing. Like we have this room almost the entire afternoon, but I need to leave like 4:25. But I know that the people may stay longer and we have other questions. So if I leave early, others will take care, Ronaldo will take care and keep with you, okay? So thank you and bye-bye.
Yeah. Thank you so much for kind introduction, and it's my great honor to be there and give a talk today. Yeah, so let me share my screen. So can you hear me well, and can you see the slide well?
Yeah.
Cool. Yeah, so okay, let's go. And before that, please stop me and ask any question if you have anything uncertain. Yeah, so my name is YY, and I'll talk about neural graph embedding today. So do you recognize this painting? Anyone? Yeah, I think some of you know this. A special thing about this painting is that it won some small state fair. But another interesting thing is like it's a AI generated painting created by Midjourney. And I think I don't need to tell you about like what we are in right now, like this whole revolution of AI methods. Like it's really good at generating like amazing pictures, and it's not just pictures, but also text. This large language model, for instance, has some capacity to reason through problems. And you've seen ChatGPT, you're probably using ChatGPT now. And it's really good at like producing amazing text. For instance, this was, I think, a prompt to create kind of parody of Bohemian Rhapsody for academia. And some part of it is like kind of too sad to show. Yeah, so it's amazing, basically. But the question is like, how does it work? Like what's happening inside this neural network? And usually these models are like a black box, and it's really hard to understand how things are working inside these black boxes. And one of the kind of approaches I've been looking into, it has been this graph embedding method that transform its graphs into these embeddings, but it also has a kind of black box nature. So in this talk, I'll talk about like how we can understand what's going on inside some of this simpler version of these neural networks. And special thanks goes to Sadamori Kojaku, who is a postdoc researcher in my group and who has done all the heavy lifting of the work that I will talk about today. So let me first talk about the power of representation learning. As you know, as we deal with more and more complex data and the need for like compute with these data sets increases, it becomes increasingly kind of difficult to kind of address them. And one of the kind of traditional approaches that if you have a complex data, we extract features and then we put them into the model and we get some insight into the data. But what deep learning really showed was that where we need to focus on is getting the right features and right representations. So that's like really important part of this whole pipeline. If we can get good representation, the prediction model may not matter too much because we can represent the data really well. So I think two important lessons from deep learning is that first, machine learning is all about learning representations. And the second, we can let the machine learn the representation. And often that's the really powerful way to get good representations. And kind of prototypical deep learning architecture look like this. You have some complex data goes in, and you have some type of encoder that encode that complex data into compressed representation we call embedding. And then there's a decoder that transforms that compressed representation to complex data back again. Language model looks like this, transformers, and then like DALI and Midjourney, all these like generative models that also look like this. And most neural network models have some part of this architecture. And then the thing is like the embedding, the compressed representation sit in the middle. It holds a lot of power. Like by going through this bottleneck, the neural network is able to extract what's the most important features in the data. And the thing is, these representations, embeddings, living in a vector space. And sometimes we can interpret that space as a kind of literal space, and we can study them. And that's one of the kind of things I will talk about today. So for instance, if you get word embedding of like all kinds of words using text from everywhere, that kind of puts these word vectors in a locations that make sense. Like here, they compared the survey result with the embedding projection. Like for instance, they asked how jazz is closer to black or white, or how jazz is associated with kind of rich people or poor people. And that kind of survey result is somewhat similar to the embedding space, how jazz is located in the embedding space. Or in this example, they studied the embedding of the words in appearing in material science abstract. And then they could discover that the directions in the embedding space actually correspond to some material properties. Okay, something is some structure of some other materials. You can find that direction in the space. Or in this example, you can kind of imagine the space of faces and then directions where you add more hair or you add more age or beard and so on. So you can discover those meaningful directions. And that means we can kind of interpret this as a kind of actual space where the faces are located and kind of related together. And this is another kind of cool example of like moving through the embedding space from like old Victorian house toward like much more modern houses. So I think this type of like ability to represent really complex data as a kind of embedding in a space, it can unlock our kind of computational imagination. So it allows us to ask questions that is kind of hard to think about if you don't have that space. Like one example is that if you're thinking about word embedding, it allows us to think about like how does word move in the space. Like for instance, the word gay has been moving like kind of drastically in the space of words, and its meaning has changed a lot. And it's easy to think about this type of questions because we can imagine the space of words where words are living in and similar words are close together. And also we can think about like scientists moving in the space of knowledge and how they move together or how they meet together, how they collaborate and so on. Yeah, so that's kind of, I think, the power of the embedding, which allow us to think about the space itself. And you probably heard about word-to-vec model, and it shows, I think it was the kind of first model that really demonstrated this power of representation space. And I'll just briefly talk about this word-to-vec and how it works. So the question here is that how to encode the meaning of the word, right? And if you represent hello or world in the computer, it doesn't contain any of these nuances, right? And the question is how to do that. And it kind of boiled down to this saying by First, who said, you shall know a word by the company it keeps. So can you guess what word should be inside this blank?
Folks.
Yeah, it's kind of obvious. It should be quick. It should be brown. It can jump. It's cunning, and it likes chicken or hens. Yeah. So what is really demonstrated is that the context is what makes kind of the meaning of the word. And one way to encode context is a kind of term document metrics. If you have a lot of documents, we can just count how many times each term appears in each document. And that gives us this kind of context metrics. And then we can think of kind of factorizing that metrics to obtain document term relevance into the product of these two vectors. And one vector represents how each document is represented by a bunch of topics and how each word is represented by relevant to a bunch of topics. And by combining that, we can kind of calculate the document term relevance. And we can think of the same thing at the more fine-grained level, which it goes to the idea of language model. So language model really asks a simple question, like what is the probability of this sentence? And good language model should be able to distinguish like more natural sentence from random gibberish, basically. So the question is, what's the joint probability of these words we are seeing in sequence? And as you know, we can use the chain rule to break it down into this bunch of probabilities. And then that means it boils down to the question of like, given all the words you have seen, what's the probability of the next word? And that's essentially the heart of the language model. So we can think of all this context that appeared before, and then we are predicting target. So if you can do that really well, and that means we have a good model of language. And essentially, that's what GPT does. Actually, it's all GPT try to do. Like, given all the tokens you have seen, what comes next? Okay, so even this like amazingly simple task of predicting the next word can give us like amazing capacity, as you can see from ChatGPT. And the idea of neural language model is that, oh, why don't we just use neural network to do that? And word2vec even simplify that by thinking about skip ground model. which is the idea that instead of thinking about every word appearing before, we can just pick one word and then try to predict the target word. Can we just skip the other words? Okay. And then that simplified that drastically. We now thinking about just a simple conditional probability that given that we saw this context word, what's the probability of this target word? And then for given context, the whole context, so we can just calculate the probability of that conditional probability using just the product of all skip-gram conditional probabilities. Okay, so that's a skip-gram model. And then you can use this skip-gram model to the whole sentence, whole data set by just thinking about all possible combinations of context and target words. And that's the likelihood function you want to maximize. And then there is another ingredient, which is that we wrote down this formula, likelihood formula, but we don't know how to calculate this conditional probability. Like given the context, what's the target word? And the idea is that if we assume that we already have a really good pair of these vector representations, we can kind of approximate that using vector operations. And we assume 2 vectors for each word. I would just call query and key vector using the transformer nomenclature. And the idea is you can think of it as a kind of database. You have a context word, and then context word has a query vector. And then you send that query vector to the database, and then try to find a target vector which key vector, whose key vector matches my query vector. And that tells us that that target vector is very likely to appear in my context. And simplest choice probably is just using softmax function to kind of approximate that probability. And then given this objective, you can train a neural network to learn those query vectors and key vectors. Yeah, so that's the word-to-vec model. You simplify this language model into skip-gram model, and then use this softmax function and 2 vectors to approximate this conditional probability. And you can also think of it as matrix factorization. You have some metrics, large metrics, word by all the words, and then you're thinking a similarity between 2 words as a kind of row rank approximation of 2 vectors, essentially, 2 matrices. So each word has a key vector and query vector. And if you take the inner product of them, that gives us essentially word-word similarity. But the important part is that we don't have to calculate these big metrics. We just assume randomly initialize these low-ranked matrices, and then use neural network to tie them directly to the objective function. And then we can get good representation, good vectors that approximate the implicitly built this word-word similarity metrics. Yeah, so by doing that, we can get like really cool embedding result. And an interesting thing to think about here is that there's no restriction what should be the word or what should be the sentences. As long as something is appearing in sequence, we can think of them as words and sentences. Like for instance, Stitch Fix, they build the word embedding model that is trained with the IDs of these pictures of the clothings, so that they can learn the embedding of both clothings and words at the same time jointly. And then they could do something like, okay, I like this particular clothing, but I want kind of a maternity version of that clothing. And then they could simply add vector for pregnant to obtain kind of similar clothings from their database. And we can also think about network context as well. So why not think of each node as a word, and then some trajectory in the network as a sentences. So we can think of like kind of graph models instead of language models, and graph embedding instead of language embedding, word embedding in the exactly same way. And that's the kind of basis of most kind of early stage graph embedding models. And the idea is if we can generate walks on a network, and that can serve as sentences that capture proximity in the network. So if two nodes are closer together, they will appear together more often in a random walks, and then their embedding will become more similar. So the most common way to do it is run many random walks, and then use the IDs of the nodes appearing in random walks as if they are words, so that we can get the embedding of those words. Yeah, so that's the base, like super basic graph embedding methods. So again, graph embedding based on this idea can be thought of as a metric factorization. So each two nodes have some similarity metric. It can be kind of proximity, conceptual proximity between these two nodes in the network. And then they can represent it by these two low rank metrics product. Okay. So I will show some interesting examples of unreasonable effectiveness of this simple graph embedding method. The first one is about kind of capturing like scientific knowledge space. And this one was done by my colleague Hao Peng and Chinka and Jerome Budak and Daniel Romero. So here we looked at the citation network. So we can construct huge paper citation network. And then once we do that, we can create random walks. So you can imagine like situation where you start reading a paper, you don't understand something, looking into that part, that cited paper, and looking through another cited paper and so on, like kind of following the citation trail. And then what we did is kind of replace them with the journals instead of keeping the paper ID. So we replace them with the journal ID so that we can get sentences of journals instead of papers. And then that gives us the embedding of journals instead of papers. And the space looks like this. So we colored them based on some manually curated categories. And then you can notice that these manual categories are pretty good in terms of capturing the space, the clustering, cluster structure. But there are also interesting things you can find. For instance, here you can see kind of archaeology and anthropology journals that form kind of island inside social science. And they are classified as earth sciences, which in a way makes sense because they use a lot of earth science methods like carbon dating and so on. And at the end of the day, it's like digging the earth in a sense. But in terms of like what kind of topic they deal with, it's closer to social sciences. And actually they are closer in the embedding space to the social sciences than earth science, but the classification is done with earth science. So in other words, this embedding space captures this type of like complex relationship between disciplines, and it kind of can display and exhibit that structure. Yeah, and we did a lot of evaluations, and they show that this embedding works much better than more traditional representation method. and it can predict kind of disciplinary categories, and it correlates well with how experts assess the similarity between field. But it can also do kind of some wild stuff. Like you may recognize this XKCD comic, where all the fields are arranged by purity, right? And we were thinking like, can we do that in the space of these journals? We put like social science and humanities on one end, mathematics and physics on the other end, and we projected every journal onto that axis. And indeed, we could see that it's exactly what we can see. We label from soft to hard science, and the sequence follows our intuition and that XKCD comic. I was very happy to sneak in that citation to XKCD comic to the paper. But interesting thing is, if you pick different poles, like social and biological, it like rearrange in a totally different way. Like for instance, EE and CS, they were very close to mathematics and physics in like soft, hard science axis. But if you look at social to biological, they're very close to social and very far from like biological science. So they change their places a lot by thinking about different axes. So you can find those meaningful axes in the space. And we can also do analogies. We pick a periodical, a conference or journal, and then we think about two poles. It can be like physics versus like computer science, or biology versus social science. And then we can add and subtract those disciplines to see where this focal periodical will move. Okay, what kind of other places will we get? So for instance, we can start from like KDD or ICWSM, which is kind of computational social science conferences, with a more KDD being more computer science flavors, and ICWSM with more social flavor. And you can keep adding machine learning while removing sociology. And then you get the EMNLP, ICDM, ICML, and NeurIPS, which makes sense. And then you can add sociology while removing machine learning to get like social forces, which is one of the famous sociology journal. And you can do that with any place. Like you start from like journal of climate, and you are adding social science and removing physics. Then you get meteorological society bulletin, and then weather forecast journal. And then by adding more physics and removing social science, you get like climate dynamics. Or like from cancer, you move into diet as you add more soft science and remove physics. And as you add more physics and remove social science, you arrive at cancer research and oncogene. Yeah, so you can do analogies, and you can verify that this works really well in the embedding space by looking into more quantitative validation. Yeah, so that was kind of one exhibit, and we've been working on kind of new way to conceptualize the knowledge space, and this is a kind of part of the project where you can see how different areas of science is organized in the embedding space. Yeah, so there was one, and yeah, and in this space, by using this embedding method, node to back, for instance, you can predict whether two authors will collaborate in the future very well, much better than traditional like link prediction method. Yeah, so the question is like, how does that do it, and why? number 2 is about random walks and graph embedding. So from network science, one of the really interesting kind of knowledge from network science is that when you do random walk, you tend to go to the hops because hops have many edges. You are more likely to pick one of them to go to the hops. So when you follow an edge, there is a bias toward the hops. So if you have a network with a core and periphery structure, then if you run a random walk, they tend to stay in the hubs way longer than the periphery. So that means the neural network will pick this up as a really important information to predict the next step in the random walk. So what we expect is that, oh yeah, this degree should be super important information that is picked up by the graph embedding method. But it turns out that Notepad seems to work fine. It doesn't suffer from this degree bias at all. And that's like interesting. Like why doesn't it suffer from degree bias? Okay. And number 3 is kind of thinking about this physical space. So this is led by Dakota Murray, Ji-Sung Yoon, and Sadamori Kojaku. And here, what we did is that we grab kind of scientific mobility data. So basically how people move across affiliations, different affiliations from bibliometric data, and then fed that into word-to-vector model. And that give us, so basically here the words are institutions, and a sentence, each sentence is a kind of career trajectory of a scientist across those institutions. So it gives us the representation embedding space of the institutions. And that looks like this. And it's like looking at the Earth from the North Pole, if you look at closely. And you get to see these very strong clusters based on the countries. But it's not just countries, it's also about like culture and language. Like for instance, Quebec is closer to France than Canada. Or like you can see kind of religious or cultural groups together. Like for instance, Portugal and Brazil is closer, and all the Spanish speaking countries are closer together, and so on. So this makes a lot of sense. But another interesting thing is when we measure this kind of distance between places based on the gravity law of mobility. So gravity law is a really fundamental framework to study human mobility and any type of mobility. And it's, of course, inspired by the theory of gravity in physics. And the idea is super simple. You are just less likely to go somewhere farther away than somewhere close. So it is expressed like this. So basically, the flux, number of people moving between two places, should be proportional to the population, the product of population, which is the most basic, reasonable assumption. And then a decay function of the distance between them. So if you kind of compare what's the predicted flux and what's the actual flux between two places, if you look at the bottom row, that's when we look at the geographic distance, using the geographic distance to kind of estimate the predicted flux. It has a lot of errors and it doesn't explain a lot of data. But if you look at embedding proximity to calculate that expectation, you get much better prediction. And you can get the same result with two very different data sets as well. And it's even better than directly optimizing for gravity law so that we can place all these institutions so that we optimize the gravity law. So that's kind of strange, right? We don't see anything about gravity law in the word-to-back function, but yet we get really, really good agreement between where these institutions get placed in the embedding space and how it's related to the expected flux dictated by the gravity law. So there must be something going on here. Okay, exhibit 4 is about clustering. So in network science, there is something called detectability limit. So on the bottom left, you can see these are two clusters of nodes that form communities. The question is, can we identify those two communities? Can we really find these two groups together? And it's very much closely related to a classical clustering problem. And the thing is, even there are two limits. One is algorithmic limit, which is this algorithm may suck, may not work as well, and they may fail at some point before we arrive at the perfect mixing, which is kind of impossible to find, and there is no structure. But due to the kind of fluctuation in the random matrix, and random matrix theory and spectral graph theory tell us that there's a kind of fundamental information theoretical limit of when we can find the communities. So it basically is translated as a kind of related relation between largest eigenvalue of the Laplacian and all the other eigenvalue spectrum. So this other eigenvalue spectrum has some width because of the inherent fluctuation in the random matrix. But if this largest eigenvalue that represent the community structure touches this semicircle, then we cannot distinguish communities from fluctuation. And that's why we have a detectability limit. And even before we arrive perfect mixing, still we have some community structure, but it's impossible to find based on the data we have. So that's the detectability limit. And it turns out that if you run node-to-back on this graph with the clusters and do clustering, it finds the cluster really well. It almost approaches the theoretically best method, which is a belief propagation. So that's strange. Why node-to-back should find those clusters so well, right? So those are my exhibit, and I'll talk about why that's happening. So the first ingredient is a negative sampling. We can go back to this idea of like key vectors and query vectors and using softmax function to approximate this conditional probability in the discussion of language model, right? So one thing I didn't mention is that calculating this partition function or this normalization term is nasty, because you need to calculate for every word combination and each time. So it takes time. So the thing is, the original authors came up with the idea called negative sampling. And the idea is that instead of calculating this normalization term, can we solve another problem, a different problem, which is, can we distinguish the true target word from randomly chosen fake words? The better we can distinguish them, the model is better. The better the model is, essentially. So basically, you're solving logistic regression problem and try to maximize the difference between its logistic function with the true target word versus a fake word, okay? But it turns out that this is quite close to unbiased estimation method called noise contrastive estimation. So noise contrastive estimation is an unbiased estimator, and it can let us to estimate any kind of probability distribution using this type of logistic regression framework. But it's slightly different from negative sampling, with one more term that reflect the noise distribution. But we can rewrite the negative sampling to kind of express that in terms of noise contrastive estimation problem. So by simple rewriting, what we get is that negative sampling is a biased estimator, and it's not actually estimating this softmax function. Instead, it does something different. It estimates a weighted softmax function with the noise distribution. So yeah, it was kind of interesting to find this kind of implicit bias in the negative sampling. But what's more interesting is like how this particular bias affect our result. So you can think of this bias as something as a kind of baseline probability, and then the embedding as a kind of capturing the information of residual that was not captured in the baseline probability. So in other words, this negative sampling is a biased estimator, but because of the bias, it removed the bias in the data. So for instance, I mentioned that random walk is biased because it tends to go to the hops. It tends to go to the nodes with a large degree. And that's an inherent bias. So if you just run random walks, it produces biased data. Okay. But because of the implicit bias in the negative sampling, that negates that random walk bias to get unbiased residual embedding. So in other words, the word-to-back method or not-to-back method was like very lucky because they didn't realize this bias, but they happened to correct the bias in the data. Yeah, so I think word-to-back model's choice of negative sampling was kind of intentional. It was just a way to make it much more efficient and simpler, but that introduced implicit bias, and then that produced better performance by negating inherent biases in the data. And there are two implications. One is gravity law, and the other one is kind of a new way to remove bias from data. So the first one is gravity law. So given the knowledge that we have that like negative sampling is a biased estimator, we can think of what exactly it corresponds to. And if you think about the flux between two places, you can write it down as a probability of being in a place and then probability of transitioning from that place to another. Okay, and you can write this way. And then with some assumption that embedding dimension is like large enough and so on, we get this formula, which is gravity law. So in other words, due to this interesting bias in the negative sampling model produce embedding that follow gravity law. So that's why it works so well with the gravity law. Yeah, so essentially this space learned from not-to-back model is a kind of optimized space where distance relationship follow gravity law based on the empirical flux data between places. So that's again kind of happy accident that lead us to interpret the space in a kind of physical way. So in other words, if you have a bunch of trajectory data, if you feed that into word-to-back model, get the embedding, you can calculate like gravity potential in the space, across the space. And you can literally apply the theory of gravity to the space. And other exciting thing is like residual embedding, which go back to the idea of like baseline versus residual. And the idea is, can we remove any statistical bias using this framework? And it's very simple idea. Instead of using this kind of null distribution, we plug in any null model we want to remove from graph embedding. So this is a kind of process. And we looked at the citation network, for instance, between journals. And here there is a very strong temporal correlation. You tend to cite more recent work, and then older work have a more time to accumulate citations. So there is a very strong temporal bias. And it's really hard to remove that temporal bias because it's hard to specify. But one thing we can do is we can rewire edges while preserving the property that we want to remove, and then use that as a null model so that we can get the embedding that is free of that null model. So we showed that if you actually do that, it tends to produce the embedding space where temporal information is largely irrelevant in the space. And then it works much better at predicting many things. Yeah, so you can read our paper. It was published in NeurIPS a couple of years ago. And then going back to the clustering result, we can use this implicit metric factorization to explain that property. So as I showed earlier, Notepad works extremely well in terms of finding clusters. Okay. And the reason why it's so good can be studied by thinking about metric factorization. So the node-to-node similarity metrics I mentioned, we can actually write it down, which is basically point-wise mutual information between two nodes appearing in random walk trajectories. And then we can use that fact to actually factorize it and calculate the spectrum distribution. And then that kind of lead us to this result where the condition where community become detectable under node-to-vec method. And it turns out that this limit coincide with the information theoretical, like fundamental limit of community detection. And that means for node-to-vec, information theoretical limit and algorithmic limit is the same. It's the optimal method, essentially, in the limit of good large enough embedding and so on. Yeah, that explains why it works so well in community detection, essentially. Yeah, so I'll skip a little bit. And then another ingredient I think Node-to-vec has is a stochastic gradient descent. And the reason why stochastic gradient descent works so well is that it has some kind of self-regularizing property. So if network is dense and you have a lot of data, your global minima and the true minima is matches. But when you have not enough data, it's more messier, and your actual global minima may not match the true answer. But the thing is, stochastic gradient descent is noisy. It produces a lot of different kind of gradient landscape. And if you take the ensemble average, it can lead us to a better solution, essentially. So that's a kind of quick summary of the idea of the self-regularization. Yeah, so as a summary, I think even this simple method, word-to-vec and node-to-vecs, are super powerful, and they present some like really interesting, unreasonably effective result in clustering, in identifying like embedding space of like knowledge space and so on. And this all boiled down to this kind of bias that has not been really acknowledged before in negative sampling, but in a kind of really nice, how to say, coincidence, that bias happened to correct other harmful biases. I mean, other biases like random walk biases, and it leaded to kind of equivalent to the gravity law, and that allow us to interpret the space much more kind of grounded way using physics essentially. And then this kind of particular mechanism can be leveraged to remove bias from graph embedding. Like as long as you can kind of create a null model, then we can remove that bias from the embedding by using this residual to back approach. And then the fact that node to back can be interpreted as a kind of factorization, matrix factorization of similarity metrics, that kind of led to the result that the detectability limit of the node to back based method coincide with the theoretical limit. And probably due to the stochastic nature of stochastic gradient descent, node to back detect communities really well. Okay, that's my summary. And I would like to thank all of my team members and all the funding organization who funded our studies. Thank you very much.
Right. Can you hear me?
Yeah.
So it's Ronaldo. Diogo had to leave. So
Oh yeah, hi.
he asked me to kind of I don't even know if there's a camera here, but anyway, so so it's nice to see you. So I mean, for the people here, so I think we met 14 years ago, so it goes by really fast. So yeah, so tells a little bit about my age, I suppose, not yours. You were very young at the time, you continue to be young. So any questions, right? Wonderful stuff. So I'll pass to Chico Camargo.
Hey, wait. Thanks for the talk. So one thing I always wonder with research like that, especially using embeddings, is the so what question. You made a very good point for the unreasonable effectiveness of it all. That becomes kind of reasonable after you explain it, but very, very clear point there. But in moments like when you showed the analogies saying that, hey, we can make analogies between conferences and papers and whatnot, in points like that, I'm left wondering kind of, so what do I know now that I didn't know before, beyond it kind of looks intuitive, you know, beyond like, yeah, it looks about right. Portugal and Brazil, one colonized the other.
Yep.
Beyond that, kind of what do we get from that? Is there any insights towards other disciplines that we can get from that?
Yep. Yeah, so very good question. I think we met before. Hi.
Yeah.
Yeah, so I think one of the value is that it kind of can let us to measure in a very different ways and think about question in very different ways. Like for instance, this kind of embedding approaches let us to imagine a space where we can put papers, journals, authors, concepts, and many other things into the same exact space. And that means we can think about like, okay, what's the distance between these people and those journals? And this is what I mentioned about like computational imagination. Like it let us kind of imagine better in a sense that you can do so many kind of new types of measurement. So in part, this effort is about making better instrument. Okay, so in a way, it can be thought of as building better telescope or James Webb Space Telescope. It can let us to see something better. It may let us to see something that is totally new. So I think that's the kind of one aspect I really like about. And other aspect is that it let us measure kind of better in a sense that, for instance, one of the results I showed very briefly is that once you get this embedding space, you can predict how people will collaborate way better than like traditional network-based method. And that means basically you can predict better. So you can predict like, there's another work I didn't introduce here today, but we have a model of how this collective of scientists or lawyers or inventors produce publications, like in terms like scientific papers, legal documents, case laws, and patents. And we have a single model that kind of simulate the whole space. And that let us again predict much better, like what kind of publication will get more citations and so on. So I think those two are most immediate things I would like to say. It basically gives us better framework for measurement that allow novel measurement. And then it simply works better in many tasks, especially prediction tasks. And other benefit is that because everything is vectors, it's like become trivial to plug in machine learning pipeline into that. So yeah. So I think those are main benefits, but a lot of it is not answering like substantive questions, but answering more methodological questions. Yeah.
So I'm going to allow myself a question before I go to just because it's a follow-up on this one, unless you, is yours a follow-up with this as well?
It's all about the same topic.
Yes, true. But I'm going to talk about prediction. Anyway, so why? So the question about prediction and the power of prediction, right? So I was wondering, for instance, obviously the way we do science and the way we collaborate today is different than how people collaborate in the 1950s, when I suppose the space was a lot more important than it is now, right? So it's much easier for me to collaborate across the ocean than it was before.
Yep.
So you're saying that this is actually, this spatial constraint is actually embedded in the graph, so I don't have to be worried about it. So the actual way the graph, so if I construct things all the way to 1950s, for instance, the spatial constraint will be automatically be more prevalent than it is now. Is this have you seen this?
No, I think that's a really interesting question that I think we should probably look into. We are thinking about like two spaces in the works I introduced today. One space is purely based on kind of topics and types of things you write about. So that's the topical space, and that's where we predicted the co-authorship in the future. And then the other space is kind of institutional, like geographical space. Okay, and we can actually put scientists in that space as well. The question is if we can combine them. I'm pretty sure that we can get way better prediction if we actually introduce that geographical information. And it'll be super interesting to see how this kind of modern technology has been changing kind of collaboration patterns in the over time. So for instance, I can see in 80s, for instance, it will be extremely difficult to collaborate like across like different continents, but now it's much less of a problem. So I expect to see the importance of that geography like diminishing over time.
Okay.
Yeah.
I'll pass on to another question here. Oh, come back.
Cheers. Hi, thanks, that was impressive. I've been wondering if you have been looking at comparing with results from topic modeling with latent Dirichlet allocation. such as the work from Louis van Haan, I think, in 2005, who has been looking at tons of, extracting topics from many research papers. I don't remember how many, but it was like the 100 topics in science or something like that. And you can have the relation between topics as well as the relation between documents through the topics, etc. Obviously, it is different because I don't think it was using context in the same way you do, because they have documents and they consider them as bag of words, whereas here you have obviously a sequence of words. So that's the difference. But I was wondering if, if there are differences in the results, because obviously here you're looking at papers. I mean, in one of your examples, you were also looking at papers and basically extracting topics from papers and relations between them. So since it's a similar study, I was wondering if you had been comparing with it, see how better you get at it. Or...
Yeah, so that's another like super great question. Like you can think of topic modeling as just another way to get embedding, right? Like each topic give us an element in the vector, and number of topics is your dimension. So I think it's basically the more traditional way of doing embedding. So in the work I've introduced today, we didn't directly compare with the topic modeling, but there's another project where we did compare quite a lot, which was looking into kind of hip hop lyrics, which is very different. But one comment about topic modeling versus word2vec is that it has a little bit different kind of flavor in a way that, so in hip hop lyrics, there are so many slang words that means the same thing, okay? And in topic modeling, it's difficult to discover that similarity, because topic modeling is, again, all about like co-occurrence. But in word2vec model, it tend to do that kind of synonym detection much better, because word2vec, how to say, it puts two words closer together if they are replaceable. And topic modeling, if two words are totally replaceable, they will never co-occur and they never be in the same topic. So I think that's a kind of big difference. And that's one of the reasons why I tend to use embedding method much more frequently than topic modeling, because there is this kind of fundamental difference. And oftentimes, the properties of the word2vec is what I would like to have in our embedding space. Yeah, but I think, I know only little about how they compare, especially in terms of like scientific space. Yeah.
I'm sure that'll be interesting to. Just reading your study and reading again that paper from 2005 and looking at differences in what it finds in the relation between topics of science. But in terms of hip hop, I'm sure that hip hop writers use thesaurus or their own understanding of synonyms between swear words, and I'm sure that they use multiple swear words that mean the same in the same songs. So there must be co-occurrence, because they don't want to repeat the same swear word multiple times in the same song. But thank you for your explanation. I understand what you meant. Thanks.
Any other questions? Well, I cannot. So another question here.
Hi, so it's interesting, this bias correction that you identify, and of course it's a bit domain specific. Have you ever looked at biological networks and whether you can repeat this effectiveness also for different biases that occur in biological networks, like protein-protein interactions or whatnot?
Yeah, we haven't tested on biological networks, but the nature of the bias and kind of bias negating capacity is kind of, it will exactly same across different network, because it's about like really basic network structure and random walk bias that just comes out of the network structure. So I think like which domain the network comes from doesn't matter too much in terms of like how this bias will affect it.
Well, I'm not sure.
But
So it could be that if you have hubs in a biological networks,
mhm.
you might not want to remove it. I mean, you might not want to have an embedding that is is not affected by these hubs because for that reason. I don't know. So it has to be investigated. So the presence of a bias is, I think it is domain specific. But I like your null model idea, which you can be flexible and you can try, identify where the bias is and compensate for that.
So if you actually want that degree bias, it's actually quite simple, because you just need to change the option from negative sampling to hierarchical softmax. Hierarchical softmax doesn't have the bias, so it's literally just switching one option in our Word2Vec model. And one thing I want to mention about this residual to back approach is that one thing I really like it about is that you can be much more explicit about what bias you are removing. So a lot of kind of Word2Vec bias removing models, they kind of try to kind of brute force to remove certain bias in the embedding space, assuming that it's kind of linear in nature. But in our case, I think we are creating much more explicit biased model that can be scrutinized as a kind of bias model. And we are actually working on a subsequent project that generalize this residual to back approach to a more kind of general contrastive learning paradigm. So that's basically creating a bias model as a teacher model to remove all the biases that this teacher model has out of the result embedding. So it can be applied to any graph neural network method. Yeah.
Thank you. Very nice.
Any other questions?
Thank you. So in your presentation, you mentioned like simple methods such as node-to-whack is very effective for very large graphs. I wonder if the hyperparameters has a huge impact, such as the length of the walk or the dimension for the embeddings have a huge impact on the result or on the effectiveness. And normally, how do you choose those hyperparameters?
Yeah, that's another great question. So we have a paper on the dimension of the graph embedding. And what we found is that like for most networks, you don't need many dimensions, and increasing dimension doesn't affect too much. So it's actually fairly safe to just use the default dimensions like 64 or 100 or 200, because most network have a very low kind of inherent dimension, while increasing it like twofold, threefold doesn't affect downstream performance much. And the information contained in the embedding space is more or less kind of comparable once you cross certain minimum number. So that's about the dimensions. So after that study, I don't worry too much about number of dimensions. The only thing, kind of the most critical thing is like, do you have enough dimensions to express the network? And other parameters, one important parameter is basically how much you train, especially in large networks. The thing is, due to the random walk bias, the nodes with a small degree, they don't get visited often. So you need to train quite a lot, much more than what you would expect to really train for every node in the network. So we had a project that deal with like large networks, and at first we didn't get like good result. It turns out that we just had to train more to get reasonable embedding. So that was one important takeaway. And Windows length, I think as long as like it's kind of long enough, again, it doesn't matter too much.
Yeah, thank you.
One final question here. So I know that we took a lot of your time. So
Thank you so much for the talk. I'm sorry if I missed something. I'm not very knowledgeable about embedding spaces, but I work with co-authorship networks. So my question is if this bias correction that you are doing with the word2vec, do you think could help to correct biases regarding the representation of different populations in the network of scientists? So for example, there is a high correlation of these nodes that have a high degree and like with the random processes pass a lot through them are like in global north countries and are main and English speaking. So do you think this bias could be all kind of corrected somehow with the node2vec?
Yeah, that's one of our kind of motivation to look into this next project I briefly mentioned. So basically, you can think of kind of link prediction kind of paradigm where you recommend people to like collaborate or assemble a team and so on. If we just use a network-based method, we'll just recommend based on what people currently have, which means like it's hugely biased against minority population. So yeah, that was one of the motivation to think about like this contrastive learning approach. Like if there is a model that produce like really biased result, can we use it as a null model to remove that bias out of it, so that that particular information, that label, like I don't know, race or gender, become meaningless in terms of like making recommendations. Yeah, so I think it's a great question. I don't think our current project will address the scope of your question, which is much more kind of broader and big. But I think it's one way to kind of approach that problem, like embedding. Can we get the embedding space where we can be much fairer in terms of like recommending someone or recommending links, recommending papers, and so on.
Thank you so much.
I think it's not like to think why again for there's a, because I told him it was the last question, but since you want to.
Thanks. I just want to come back quickly to the beginning of your talk about art. What do you think? So at the moment, I guess artists are, confused and a bit disappointed by this technology that might replace their work. But I think it's going to transform the work of the artist, obviously, and lead to more exploration of our imagination. Do you think the artist is the one who creates those tools like sample diffusion and Dolly, etc., or is the artist the user of those tools that can come up with interesting prompts?
Yeah, good question. I mean, it reminds me kind of the original computers when there was no personal computers. So now we all have these powerful computers, but like early days, there were actual people who do all these computations. And I think those jobs are largely gone. But still, I think we are using computers to produce amazing stuff. So art will probably fundamentally change. But at the same time, I think if you think about modern art, it's not about like how well you draw anymore, right? It's all about ideas and kind of creativity and so on. And at the same time, kind of there's also a niche where people producing like physical art pieces. So I think that's where a lot of kind of current art market will diverge into. Like now it become like trivially easy to produce like realistic digital painting. So that may be gone. But that doesn't mean that other parts of the art can thrive, or kind of totally new genres will emerge. Like for instance, I watched one day this amazing kind of music video that used like stable diffusion to like go through a life of a person with just amazing kind of frame by frame generative models. I think a lot of these will still be super valuable and will be hard to create given the creativity required to do that. But yeah, who knows? I think we are doomed with with all these crazy AIs and yeah. So I don't know.
Thank you, YY. So thanks again. So just round of applause.
Yeah, thank you very much for having me and
See you,
staying
even
here
if
and
it's-
ask questions. Yeah.
Even if it's virtually, maybe next time. I mean, hopefully you're going to Net. I'm now going Net side.
I haven't decided yet. Maybe, probably.